if you have 1,000 computers on the cloud, there will only be 1,000 users accessing the system. So if any other user comes in, they will have to kind of wait, or just queue up or get some time slice of the total time you can actually access the computer. So many things like that, right? So overall, they will see a reduced performance, right? So in the extremes case, security usually comes at the cost of performance. The other scenario here would be that, let's say you have some data, right? You are saying that you want to completely secure this data. So you can actually secure this data by running it through some encryption, decryption algorithm, right? Now these algorithms are very complex, and even if you're using some very good VLSI technique, these algorithms take several cycles, right? Encrypting and decrypting. So whenever you kind of run every data you get from these machines through encryption and decryption engines, you end up spending more cycles to get these data. So end up basically increasing security, but reducing performance, and maybe sort of increasing the power consumption, right? So ideally, what you want is that you have to increase security while either maintaining or increasing performance, maintaining or reducing the power consumption, right? You shouldn't have to reduce performance. You don't have to trade off performance, right? And that is where the essence of computer architecture comes. So architecture, what it enables you to do is that it enables you to design systems in such a way, using some clever techniques, to provide security while somehow giving you maybe similar or higher performance, and without kind of an increase in power, right? You either consume the same amount of power or reduced amount of power. Okay, so why this is important? So I don't know if you are reading the news nowadays. A lot of different countries. So there are several factors here. Sometimes there are state actors, right? So there are countries in Asia, right? Some countries like North Korea, some places in China, and some very bad people, right? Who kind of design things like ransomware, right? What they do in these um, sort of uh, uh, applications is that they will somehow, right? If you were to um, use their applications, go to a website or something, um, encrypt your entire disk, right, and ask you for ransom, right? And then you have to pay them using bitcoins, in which case they will give you the key to decrypt your disk. If you don't pay them, then all your data would be gone, right? And what they have done is that they have threatened several people, several big cities, several countries by encrypting some very valuable data and not giving them the key. So if you encrypt something and not give somebody the key, that data essentially is basically not recoverable, right? So lately, since 2018, there has been an increase in the number of ransomware incidences, right? And this is usually used by countries like North Korea to as a source of income, right? Because they are under sanctions, they keep kind of proliferating these ransomware across even regular people like you and me. We can have ransomware, and then they'll tell you like pay us 2-3 bitcoins to give you the key, right? And when they give them 3 or 4 bitcoins, right, they will give you the key, and then you can decrypt your computer and get all your data back, right? There has also been an increase in the number of cold boot attacks, right? So what cold boot attack does is that people usually go into the data center, they break into the data center, they remove the DRAM, right, the DIMM in the data center, they spray it with liquid nitrogen, so it becomes very cold. What happens then is that the data that is present in DRAM remains there, right? Then they actually use a machine, right, to read that data and get a lot of confidential information, and people have shown that this is also increasing, right? And we need ways to kind of store data in such a way that people cannot actually recover your data, right? So that is a challenge, right? And very lately, people have looked at problems. So these ransomware attacks usually happen on SSDs. Okay, so your hard disks, your SSDs are very vulnerable to these attacks. These cold boot attacks happen on DRAM, right? Your memory sticks are vulnerable. And very recently, people have shown that there are like attacks called Meltdown and Spectre that target CPUs and caches, and they exploit some properties of CPUs to leak um, some vulnerable data about users, right? And these are the reasons that kind of made me very interested in memory security, right? Because what is a memory system? Memory system is a place where you store your data, right? So in any sort of attack, right, you always target your memory system, right? You might use the CPU, but eventually, if you want to get access to data, you target the memory system, right? And once you target the memory system, if you can get access to the data, good. But if you can't, then it's essentially useless, right? You foil the attack, right? So how can you kind of protect uh, against data theft in these memory systems is a very interesting area, and something that computer architects can investigate. Okay, so essentially what I was looking at was hardware oriented security, right? So some of these things you can actually fix using software. The problem with having software fix is that software has a very different point of view, right? Let's say that you have some software that tries to prevent against ransomware. It's possible that the ransomware um, can fool the software, can get evolved, and the software cannot catch some ransomware and things like that, right? But if you look at a hardware, it's very low level, right? And hardware kind of works at very small granularity, right? It works at bytes or bits of data. So at that level, if you can somehow fix things, then you don't need a software fix, right? It's a more efficient kind of technique. So that was why I was looking mostly at hardware-oriented security, right? And these are probably the areas that I was broadly interested in. Obviously, today I can't um, um, talk about all of them, right? And I'll try to talk about two problems on one on preventing cold boot attacks, and second on preventing replay attacks, right? And another problem, the third problem on side channels, we can talk about later, maybe at some other time, um, because just these two itself is a large amount of um, uh, literature. Okay, so any questions until now? If you have any questions, just feel free to ask. There's no need to um, keep it to the end. Okay. Um, Thank you. So I will start. Okay. So the problem here that I'm going to use a lot of my, I'm going to draw and write a lot in my slides as well. One of the advantages of being online and having this nice software iPad is that I can actually write things on my slide deck, and we can actually be more interactive in our presentation. So let's start doing that. So one of the things that I wanted to address uh, was something related to do with um, new technologies. Okay, so these are called NMT. Okay, so before that, let's go over some background on how a computer system actually works. Okay, so usually what happens is that you have an application, right? This is a for loop, right? You compile it, right? Let's say you used GCC to compile it. Then you have a binary, right? If you look into the binary, right, there will be like move, add, subtract, instructions, right? So the compiler would generate a binary with a lot of, if you kind of look into it, and if you decode this binary, if you were to decode, you will kind of get all these instructions present inside the binary. Now, what happens is that when you, if you look at your, let's say you are using an AMD chip, this binary, right, is executed in one of the cores in this chip, right? So essentially that's what happens. Now, if you look more closely, you will see that this chip is now connected to a memory system, right? So there is a DRAM based memory system, right? And what happens is that this binary, right, would actually occupy some space in this memory system, right? Which means that if you were to kind of look more closely, and if you kind of flatten out the address space, you will see right, that this is your application data, this is your array plus data structures and whatever, right? So all of your heap and stack, right? So a lot of the data you're working with, right? So usually everything is stored, all the data is stored here, right? And that is how a von Neumann machine works. So I'm sure that you all have you all know what von Neumann machine is. In a von Neumann machine, there is data, there is compute, right? So here there is data, this is compute, and you keep cycling your data through the compute, right? It's like a factory, right? And your compute will process this data and write your data back. So you take your data, process the data, and write it back, right? One very good example would be that let's say that you want to find the factorial of numbers, right? What will happen is that you will provide input as 1, 2, 4, 8, or whatever, and output will be the factorial, right? And the compute is actually computing the factorial, right? And this output factorial is stored again in memory. So if you're actually having a large array or a large structure or whatever, that would be stored again in the memory, right? Now, this is a very simple example. Now you can think about very complex examples, right? Think about what happens when you have bank transactions. What happens when you have something which is very more significant, right? Let's say something in the defense area. If you have, you can have any sort of application, right? That works on any sort of data, right? So So right now, if it's a factorial example, it's more easier to understand, but you can have any important application, right? It can be maybe some application that launches a spacecraft to space, and it's also using something like this, right? It's working on some data, right? So one key thing that you need to understand here is that, I mean, there are two or three key things. The first key thing you need to understand here is that the speed at which your compute works, right? Let's call it T, right? Depends on the bandwidth at which your data comes in, right? Let's call it B, and the size S, right? So if this is slow and this is small, then you can't work with a lot of data, right? So what people usually do is that they keep scaling memory, right? By scaling, I mean that they keep reducing the feature size. I'm sure that you have studied that in VLSI. As you keep making these cells smaller, you can make this memory capacity larger and larger. So you can have memory which is like when I was in my undergrad, we would buy DRAM sticks um, of 4 GB, 4 gigabyte in size, right? I have not heard of, in 2007 or 2008, we did not hear of anything that is more than 4 GB. Right now, we can buy sticks. This is 2006. Right now, we can buy sticks of 32 GB in size. It's 2020, right? So over time, because you were able to make these cells smaller, right, we were able to scale the memory. But at some point in time, we cannot make cells very small. And rather than using DRAM as a technology, we need to use some new memory technology, right? So the new memory technology that we are trying to look at today is PCM, which is phase change memory, right? So what is the advantage of phase change memory? Phase change memory is very high density, right? So when you get 32 GB of DRAM, at the same time, using the same amount of area, you can get up to 256 GB of PCM. Very, very high capacity. So think about it this way. If you have a very high capacity PCM, you can have newer and newer applications, right? Applications that have very, very large footprint, you can actually make those applications because now your memory capacity is very large, right? You're not bound by capacity, right? So that is definitely a very big advantage. And you can no longer have to rely on DRAM, right? Now you can just not use DRAM and use this very large capacity PCM, right? And because DRAM is not very, it scales very very poorly, right? It scales poorly. Whereas this scales well, right? Because you can have very large capacity, right? So this is the good thing about PCM, okay? Now the bad thing about PCM is that it retains data for months, right? So in DRAM, the moment you remove the DRAM memory stick out of the computer, in about 5 minutes, all the data will be gone. So if you have an attacker that has access to data center, they can remove your DRAM stick, that will put it in liquid nitrogen or whatever to keep the data inside the DRAM chip alive for 1 or 2 hours. But for PCM, even without doing anything, right? It keeps the data for months because PCM doesn't store data based on charge, right? DRAM stores data based on charge. PCM stores data based on the state, right? So there are a couple of states that the material inside PCM can be in, and that state kind of just remains as it is, even if you remove PCM out of the computer, right? The other bad thing in PCM is that the more bits you write, the lower the performance. Okay. So if you, because each bit you need to change the state, right? You need to make it from one state to another state. It's not as simple as storing a charge. You need to push a lot of current and change the state because that is a high powered scenario. It will take a lot of time for you to write bits. The more bits you write, the lower the performance. So if you have to toggle a lot of bits in the memory, the performance of PCM will be significantly lower than DRAM, maybe 4 times or 5 times lower than DRAM, right? And the more bits you write, the lower the lifetime. So PCM is like SSD, right? After some time, the bits that you write to become spoiled, and you can't use them after some time. So let's say that each bit can be written only 10,000 times. After 10,000 writes, the bits will get spoiled. I'm just giving an example, right? It's much more than that. So, and DRAM, you can keep writing, no problem, right? Because you're just storing charge. Whereas in PCM, because you keep changing the state every time you write, it's not a very good memory if you have to keep writing many things a lot of times, right? So there are good things and bad things about this memory. The good thing is that it scales well. You can have very large capacity. The bad thing is that it retains data for months. Very bad for security. The moment, let's say that you're using PCM on your mobile phone, right? Um, and that gets robbed. Very easy for the hacker, even if you have password or whatever, right, to get your data because it can just remove the attacker can remove the PCM and just read the data content without any issues. The second problem is that as you keep writing, the lifetime reduces. And if you have to write a lot of things, your performance also reduces. Okay. So any questions until now? Did you understand um, what what the new memory technologies are? What are its problems? And where does the memory and the compute fit in? So there is a strong motivation for new memory technologies, but there are also these other problems associated with it. Right. And my talk is going to be the first part is going to be focused on PCM and solving uh, these security concerns, right? Right. If you have to retain data for months, that is security vulnerability. If you have to encode bits and if they have to be written more frequently, then it reduces lifetime and reduces performance. So basically, security does not have to come at the cost of performance and lifetime. So we have to look at ways in which we have to increase security without affecting performance and lifetime. Okay. So do you have any questions until now? Any broad questions? Feel free to ask. Don't have to be worried. I'll try to answer it with as much details as possible, so you don't have to be worried about the question. No questions?
No questions.
Hello?
I think no questions.
Yeah. Okay. So
Prashant, how this PCM is constructed? How we construct it?
so they constructed using something called as some material called as a calcinogen. I don't even know how to pronounce it. Calcinogenide material. Um, in that material, if you pass current through it, it becomes from amorphous state to crystalline state. So amorphous state, so something like this. So usually what happens is that let's say this is the PCM cell. This is also a very simple diagram. Obviously, it's a little bit more complex. Right? So this cell can be in, it's made of some calcinogen. Maybe I'm spelling is incorrect, but it's a material called some calcinogen material, wherein this can be in two states. It's crystalline or amorphous. Crystalline will give you low resistance. Amorphous gives you high resistance. So depending on whether it's crystalline or amorphous, you will get low or high resistance across this part, which means that the V measure, where you measure uh, your voltage across the cell, will differ based on whether it's in C or A state. So you can say that C is binary 0, A is binary 1. So you can store data in that way. But every time you have to change the state, you have to pass a very high amount of current to change the state. So if you want to go from amorphous to crystalline, you pass a high amount of current for a short time. If you want to go from crystalline to amorphous, you pass a low amount of current for a long time. But I don't know more than this about PCM. So right. And because of the fact that you have to keep pumping current for different durations of time, eventually the cell becomes spoiled after like writing maybe 200 million times, right? 100 million times, then the cell becomes very weak and it becomes spoiled because you have to keep having these different currents passing through it over time.
But it's a non-volatile. Yeah?
Yeah, it is non-volatile. So that's why it retains data for a long time, because the moment you have changed the state and you don't do anything, right, it remains in that state. So later on, if somebody gets access to your PCM memory, they can easily read its contents because it does not change state unless you pass current over it again.
Thank you.
Yeah. And right now, I think there are two or three companies are already producing these kinds of memories. Um, um, and usually these are employed in server systems, which require like very high capacity memory. So some companies are already having solutions with PCM in them to act as a replacement to DRAM. Okay. So before I go to the
Sir, I have one question.
yeah.
Actually, RAM memory, we have some write operations we can perform. How much write operations we can perform in this PC memory?
Not very much, right? So usually in DRAM, you can say you essentially have infinite writes or greater than 10 to the power 16 writes, right? You can keep writing without any problems, right? Because in DRAM, it's basically a capacitor cell in which you just place some charge, right? And you write to it, right? So the presence of the charge, if charge is present, if it's a 1, if the charge is absent, it is a 0, right? Very easy for DRAM. But for PCM, you can only have 10 to the power 6 to 10 to the power 9 writes. Now, this might not appear to be a lot difference, right? But these are powers of 10, right? So this is like, this has like 1 lakh lower writes, I think, or 10 lakh lower writes as compared to DRAM, which is significant, and you have to employ this on real machines. So that is a problem. And people in the VLSI domain are looking into ways in which you can make PCM cells more write efficient, right? But yeah, this is definitely a problem. Right? This is because when you write into PCM cells, you're affecting the state of the cell. You're not actually working with a charge, right? Like here, you're working with a charge, but here you're actually affecting the actual state of the cell. So when you do that, you can end up um, breaking the cell very easily. Right? You can spoil the PCM cell very easily because if you keep writing, it ends up very frequently, like say 10 to the power 9 writes. You might end up having a cell which is just a broken cell. Whereas in DRAM, that's never the case, right? You can keep writing without any issues. Does that answer your question?
Yes, sir. Yes, sir. That means life is less here, right?
Yeah, very low
We can
lifetime.
form less number of writes. Yeah. Okay.
So that's why there is a lot of research has focused on, let's say you have PCM, and some people have done this already, right? You place some sort of DRAM as a cache in front of it, right, to buffer writes. So DRAM will take care of will take all of the write intensity inside it, right? All the writes will go here. So that PCM will only see a few amount of writes. So DRAM, because it's smaller in size, it can probably just act like a buffer. And PCM, because it's larger in size, can just somehow have fewer writes somehow. So a lot of people have tried to do that, but I guess the solution here is a little bit more difficult, right? Like because the difference between the writes here and here is very large. So you need some very good solutions. Mostly this will come from circuit people and device people. Right? It'll not come from people like me who are more in the systems level, right? So device people have to come up with different materials for PCM that can kind of tolerate more writes more efficiently. Okay, but on that topic, I have to deviate a bit. So if I were to use the system, and this is an open question to everyone in this meeting, if I were to use the system, how do you think I should? How do you think I should prevent my data from being stolen? Let's say, um, let's say I'm using. Oh, let's say I am using PCM as the primary memory system, right? This is my primary memory system, right? I have written some data in this. If I were to write data in this, right? Like I mentioned to you, this data is going to be remaining inside it for months. Um, And this could be a lot of data, maybe 256 GB of data. And let's say this is in your phone. Eventually, your phone gets stolen. How do I prevent my data from getting robbed? What do you think? I'm open to suggestions. Let's say this is your password, right? Let's say these are your passwords. And this is maybe your bank details. How do you think we can prevent your data from getting robbed? Because now you can't get your phone back, right?
So both software and hardware solutions can be used.
No, you can just say like whatever, right? Yeah, anything is fine. I'm open to any any suggestion.
Sure. Okay. Encryption, encrypt,
Yeah,
cryptography
so you
kind
can
of thing.
encrypt data, right? The good thing about encryption is that you can do something like this, like what Rathod sir suggested, is that you have some encryption key here. This key is a secret that only that even if you steal the phone, the person cannot come to know because it's kind of encoded in the hardware, right? So even if the person tries to uh, get this data, right, because all of it is encrypted, this data will not make any sense to that person. So that person will see only garbage, right? Like all sorts of 0 and 1, but they will not make any sense. For instance, if I were to write the message hello and store it in PCM without encryption, if there is no encryption, I can read hello, right? No problem. Because the moment I read your data, it shows hello. But if I were to use hello, you encrypt it, you will write some weird number, right? And when you read this, you don't know this means hello, right? Because you have no access to the key. The key is encoded in the hardware. So if you can encrypt data and store it in PCM, then you can easily, um, well, you may not be able to recover your phone, but at least your data is safe, right? Because nobody who has stolen your phone
But
or
sir, encryption is a part of software, na? So how it will do for the that PCM memory?
no, encryption engine can be a part of hardware as well, right? You can always have encryption present at the PCM controller, right? So let's say, um, so what is encryption? Encryption is just a set of mathematical operators, right? What you do is that you take a certain key. Let's say you're using AES encryption, right? You take the key is in the hardware. You take your data, the data that you're going to store inside PCM, right? And using the data and the key, you can use the AES engine on the hardware to get, this is called plain text. You can get something called as ciphertext, right? Now you can obviously employ software to do encryption, but the logic of encryption can always be implemented in the hardware without a lot of overheads, right? One very simple example um, that probably um, is true even now is that if you look at your mobile phones, most of your wireless um, modulator and demodulator, right, on your phone, when you actually make a call, they already have an encryption engine inside it. There is no software in your Android phone or your iPhone or wherever that actually does encryption when you're making a call. That modulator and demodulator in your phone is a hardware encryption engine. The hardware encryption will simply take whatever data is going out of the phone, encrypt it, right, and make it a ciphertext and send it over the network. You can use the same engine inside your controller for PCM before you write to the PCM, right? So basically, whatever data you're writing to PCM, you can encrypt it. Does that answer your question?
Yes, sir.
Yeah, so you don't actually have to wait for the software to do it, right? In fact, and this is a very good topic. I guess Rathod sir would know more about this. Is that if you use any sort of very efficient encryption algorithm, if you can design it in VLSI using some very clever circuits, it's a very useful invention, right? Because it's used nowadays because of the increase in the number of devices. Many IoT devices are there, drones, many things are there, right? So you want to encrypt things very efficiently in hardware. Software encryption is usually not as efficient because software usually works on large amount of data. Right? The software you see things like files, very large data, or large amount of like large pages and things like that, right? Whereas in the hardware, you see things in terms of just bytes, right, or bits, and you can possibly encrypt them at a more finer granularity. Right? And the second advantage is that hardware, if you make a chip, right, people can't break into that chip, right? You cannot find out where your encryption engine is and find out the key. It's very difficult. But if you have a software, people can break your software, right? You can always have even big softwares like Microsoft Windows, Linux, all these things are very prone to hacking, right? So software is always vulnerable because um, it's a little bit more open to people. Whereas in hardware, if you kind of make a chip that has all of these components, it's very difficult for you to kind of break that chip, probe inside it, and see exactly what the key and the ciphertext and the data values will look like. Because the moment you break the chip, it will stop working, right? The moment you kind of try to open the chip, it will most likely just stop working. So if you do some sort of hardware encryption, then you can somehow ensure that the data inside PCM looks like garbage, right? And only you and you only can decrypt that data, right? Nobody else who has access to your data can decrypt it, right? So that's a good thing. So even if your mobile phone gets stolen, your PCM memory inside, yeah, it is similar to PUF, I guess. But here encryption is a little bit more complex, right? There are many forms of encryption. I don't know if you have studied this in your wireless class. You have AES, you have RSA, and then you have several other forms now. And the goal there is kind of to implement any of these encryption techniques in the hardware, right? Whereas I think I'm not exactly sure how PUF actually works. Any other questions? No questions? So for the time being, let's just assume that we have some sort of a hardware logic that can encrypt things. Okay. So there are good things and there are bad things about encryption, right? The good thing about encryption is that the moment, let's say it's my phone, I use my key to encrypt data. I can give my phone to any of you, right? And you cannot decrypt that data because my phone, only I have the key to my data. And none of you will have the key to my phone's data, right? Um, so that's a good thing. The bad thing is that encryption has this property called Avalanche Effect. Can you guess what this is?
Generally, it is a multiplication of charge carriers. I don't know how it is related here.
Yeah, so usually what happens is that let's say that you wanted to encrypt this value. (64 bytes). Right? When you encrypt it, and this is true for any encryption algorithm, you will get a roughly equal proportion of zeros and ones, which means that 50% of your data would be zeros, 50% would be ones. So you will get something like right? So you'll get 64 bytes, sorry, of data with equal proportion of zeros and ones. Remember, in your input, you had all zeros, right? All zeros you had. But in your output, you have 50% zeros and 50% ones, right? So a very good encryption algorithm will make sure that your output looks as much garbled, as much random, right? This is appearing very random, right? As possible. Okay. Now what you do is that you say that I want to change just this one bit, right? Maybe you have a for loop in your code or something, right? You are incrementing I equals I plus 1, right? So you make it from I from 0 to 1, right? So what will happen is that your new data is 0, 0, 0, 0, 0, and all the way, and then 1, right? Which means your original data changed from this to this, right? Yeah. So what do you think the output will look like for this new data? Would it be just a 1-bit change on the output, or would it be a different output altogether? So when I just make 1-bit change in the input, what do you think the output will look like? A completely different output, right? Completely different. There's no way you can guess what the input was. That's the whole point. Many bit changes, right? So what will happen is that this will become 0, 1, 0, 0, whatever, right? Now what I want you to pay attention is this, right? Remember, we were encrypting, and this is PCM memory. Right? Right? So without encryption, if I were to use PCM, I can store this data and change this data from 0 to 1 by just changing 1 bit, right? So I am not going to affect its lifetime a lot, right? Because only 1 bit is changing, right? I only changed this bit. So the lifetime has not changed a lot, right? Only this bit is affected. Right? Second, in terms of performance, I'm only writing 1 bit, right? I'm not changing any other bit. So I can do very fast writes, right? But I cannot encrypt, right? But if I were to use encryption, see what's happening. I'm changing all the bits or 50% of the bits, which means that my performance is going to just go down, right? Because now I need to change the second bit, the fifth bit, the 10th bit, 15th bit, 13th bit. At least 50% of the bits would change, either flip from 0 to 1 or will flip from 1 to 0, right? So the cost of encryption is one, you reduce performance, and two, you reduce lifetime, and possibly three, you increase power, right? Because now you're flipping many bits, right? So making PCM secure is not an easy task, right? Because if you were to make PCM secure, you would end up keep changing a lot of bits. When you change a lot of bits, you reduce performance, you reduce lifetime, you increase power. Alternatively, you can keep PCM not secure without encryption, and you can just change one bit, right? So one of the things that I'm going to talk about today, maybe the only thing I can talk about today, given that we have only 1 hour more, was some ideas on how to fix this problem without actually reducing performance and lifetime by a significant amount, right? So that's basically what we're going to talk about today. Do you understand the problem? Any questions? Right? So this is definitely an important problem, right? Because think about it. If somebody has to ship PCM, they most likely have to provide some sort of encryption because people are not going to buy their product. But if they were to provide encryption, then their product will be very low performance. So nobody again is going to buy their product. And if they were to use encryption, then it is going to give them very low lifetime because many bits are changing for each write. Because many bits are changing for each write, their lifetime is going to be very poor for that product, right? So it's a double whammy, right? You either don't encrypt and sell the product, or you encrypt and then sell something that is going to give you very low performance, low lifetime, and higher power, right? So the first thing that I'm going to talk about is this work that I did some time ago in my PhD, and it's also a very good problem about how to have write efficient encryption for PCM, right? And hopefully this kind of thing should inspire all of y'all to look at a much better solution to actually provide encryption for PCM, right? Or any sort of similar memory technology, right? This does not require you to know what encryption is, right? You should only know that a lot of bits could change. But think about a way in which you can have this clever way to store data. Maybe you can store some data in DRAM, some data in PCM. Think about techniques over your undergrad if you have time, right? On how to do this efficiently, right? It's definitely a very important problem. So I can tell you what I did, and this was published in ASPLOS a few years ago. It's a very good conference um, on how to kind of um, uh, uh, fix this problem, right? So can you think of ways in which you can solve this problem? Can you think of any? I want some answers from you. Can you think of ideas on how to fix this problem? So here the problem is that the moment one bit changes, you change all the bits. Right? So how do you think we can fix this problem?
can we stop that one bit change? It's not possible. That is going to change, right?
Yeah, that is going to change. You cannot stop. You cannot stop that.
Then we can stop only propagation, that change, bit to bit change.
So
That chain we need to break, no, basically.
yeah, so one thing you have to do is you have to break this, right? You have to break this
Chain.
the big problem into like a small problem, right? Wherein you divide this to smaller regions. That way, a one bit change will only affect a small part of the region. So correct, right? So you need some sort of. So I think of this problem like let's say you have a huge dam, right? And somebody poisoned the water in the dam, right? If you have a very big dam, all of the water will get poisoned, right? But if you had smaller dams storing the same volume of water, then if your poison will only affect one small part of the dam, right? Smaller dam, it will not affect other dams. So you want to encrypt this in a piecewise manner, right? Wherein you a change here will not affect things here, but these are still encrypted, but using some other key, right? So that is what we were looking at in this work, right? So what we want to do is that, so here again, like the same problem is emphasized, like bit flips are expensive, right? It affects lifetime, power, and performance, right? So PCM systems are usually optimized to reduce bit flips, right? Usually you want most systems only flip 12% of the bits, right? Uh, it's basically because of locality, right? If you have like a for loop or a while loop or any sort of counter, you keep incrementing the counter, which means that you just change 1 or 2 bits in the counter, right? You don't actually change the value significantly. So most times the bit flips account for only 12% um, um, of your total uh, uh, number of. So you want to kind of reduce the number of bit flips basically. But like I mentioned, PCM systems are vulnerable to attacks, like something like stolen module, wherein you can have your mobile phone being stolen, or you can have PCM sticks being stolen from your computer, right? But if you can secure it using encryption, right? Like we mentioned, you can encrypt things. Once you encrypt things, if you even if somebody steals anything, they can't actually find it out. But encryption increases bit flips from 12% to 50%. Like I mentioned here, usually 50%, a very good encryption algorithm will flip 50% of the bits, right, all the time. So once it becomes 50%, it's like a 4x increase in bit flips, right? Which means that you're going to spend 4x more time to write the bits, 4x more power to write it, 4x lower lifetime, because now each write is actually affecting 4x more bits, which means your lifetime is going to reduce by 4x, right? The key insight in this work was to re-encrypt only the modified words, like what Inderjeet actually mentioned, right? If you can divide this into segments, you can try to re-encrypt only those parts of the segments that are modified, right? This helped us reduce the number of bit flips from 50%, 23%. It's a significant speed up, right? And it also affected lifetime. But re-encrypting only modified words on paper sounds easy, but there's a lot of finer details in it, right? Like how do you keep track of what words were modified? How do you keep track of which words were encrypted, right? So that is something that we're going to find out. So this was already explained, right? Usually what happens is that in PCM systems, how writes work is that you have something called as data comparison right, also called DCW. So let's say in your cache, these bits have changed, right? So what your PCM system does is that it will read the data in the memory, it will compare it with the data in the cache, right? So it will do maybe an XOR. So if the data is similar, the XOR will yield a 0, right? So only for data that is changed, it will tell you that you need to write those, right? So you will end up writing only these bits into the memory. Okay. Then there is also called as flip and write. So let's say that you have to write too many bits to memory, right? You will have a technique called flip and write, wherein you will say that whatever I am writing to memory, it's flipped. So I won't go into details of that, but what happens there is that this helps. Flip and write will help you reduce the number of write bits that you're writing to memory. Okay, so it looks something like this. Let's say that if you were to not use flip and write, you would end up writing all of this. But if you were to use flip and write, you will say that only this is written and everything else here is flipped. Okay, this is not very important. These are like kind of two different techniques that were proposed to reduce the number of writes into PCM, right? And these two optimizations were found to reduce the amount of bit flips to 10 to the 12%. Right? It was not very high because of these optimizations, the number of writes, right? So like I mentioned, you can have some attacker steal the data, right? And then probe that data, right? Or you can have an attacker that snoops the bus, right? Like using some devices, right? And if you can snoop that bus, you can actually get the data that is present on the device, right? And this is an actual PCM module, by the way. This was proposed and invented in UCSD. They actually have PCM modules there, and this was proposed in 2015 or 2014. It's a long time ago. Right? Now it's already commercially implemented. Okay. This is usually used in gaming controllers, right? In gaming controllers, you can snoop PCM the bus to kind of figure out the keys for certain games, and then you can use that. Some software can use that to kind of make most games available to you for free and things like that, right? So as manufacturers, they want to prevent against these stolen memory and bus snooping attacks, right? And like I mentioned, if you had memory encryption, right? Encryption causes 50% of the bit flips on each write. So even if you were to modify some bits, encrypted data would just look garbled, right? Completely, um, uh, completely garbled in the sense that you can't make out what is written. You will just read a bunch of ones and zeros. And the only way you can decrypt this is by you having the secret key that you have on your computer. Right? So there's no way to decrypt your data. Okay. So this is good, right? But like I said, there's the avalanche effect, wherein you flip any other bit, this changes even more. So it keeps changing. So it's a lot of changes in terms of bits, which affects the lifetime of PCM, right? So it becomes very write intensive, right? Like I mentioned, PCM is very sensitive to writes. It can only have 10 to 100 million writes. It's not like DRAM, wherein you can have so many writes. And because it is write intensive, the moment you start encrypting things in PCM, you have this avalanche effect, right? And what you want is to overcome this avalanche effect, right? So this is the comparison so this is on real data, right? If you use real workloads, if you see 0% is some 50% is somewhere here, right? Somewhere around here. If you have no encryption, you use these techniques, you literally see on real workloads, like if we actually ran different applications and we saw that when you don't have encryption, we were able to use PCM as it is. When you had encryption, we had like a 4x increase in the number of writes, right? Including even if you use like data comparison write or flip and write. So we had to get, so before we kind of go into details on how you actually encrypt things inside in the hardware, I want to give you some background on what counter mode encryption is. Okay. Do you know what counter mode encryption is? Does anyone know what counter mode encryption is? Nobody knows that. Okay. So in counter mode encryption, what happens is that, let's say, okay, let's take a scenario wherein you have regular encryption, right? You take data D, right? You um, you pass it through an AES engine, right? You take the key and you get data E, which is encrypted, right? Now, when this D becomes D dash, you get E dash. So as D changes, your E also changes, right? This is found to be not very secure because what happens here is that there is only one thing that changes, right? Only D changes. Key remains the same, right? Because only one thing is changing and the output is changing based on that one item, this is not very secure. So what people did was that they added a third component to the input. They added something called as counters. Okay. So every time your D changes, let's say D becomes D to D dash, right? Your counters get incremented by 1. And that is used as an input to generate E to E dash. So every time you keep updating D, your counters keep getting incremented. So that is adding a little bit more randomness so that E keeps changing without just having one variable change. Now you have two things changing, right? Every time you write to D, your counters also change. So your E it depends on both of these. Okay. Now the key part here is that these counters are stored in memory as well. So you store these counters next to your data. So if this is the data, this is the counter, right? So every time you have to encrypt the data, you read the data, you read the counter, you encrypt the data, you write it back, you increment the counter, and you write it back. And you use the key to encrypt this. Okay, so this is very high level idea of what counter mode encryption is. Okay, so like I said here, a direct encryption you will have a key, you'll have the AES engine. So here I looked at AES, but you can have any sort of encryption algorithm, right? Right, and what you will do is that you will use the encrypted data. So this is when you're reading data, right? When you are reading data, you take the encrypted data, you pass it through the AES engine, give it the key, and you get the regular data. This is how decryption works, right? So your AES is now in the critical path, right? You can have something called as a pad-based decryption, wherein you use the key and you generate the AES pad, right? You use the encrypted data and you XOR the encrypted data with this pad, and you get your uh, regular data. So this is not very important, but I'm just saying, right? So you can actually remove your AES decryption of your critical path, because you can generate the pads and keep them beforehand, and you can use the encrypted data with the pad to get your regular data, right? So you need unique pads, right? So what the attacker can do is that the attacker can somehow just pass zeros into your AES engine, right? So it can just keep passing zeros here, right? It can trick the AES engine and it can try to get the pad value, right? And using that pad, learn that pad and decrypt your data. So this is one way to break your AES encryption algorithm, right? But if you were to use counter mode encryption, if you were to have a different pad for each line and have a counter for each line, then even if the attacker finds out the pad value, because the counter for each line will keep changing every write, it's very difficult for the attacker to figure out what the decrypted value will look like. Right? So that is an advantage of counter mode encryption, and it's not related to this work, right? This is something that the security people in the security community have already investigated, and we are just using counter mode encryption in this work. So if you were to use counter mode encryption, you have the counter for each line, and simply guessing the pad value without the counter is useless. And the counter for each line keeps changing every write, so you can't guess what the counter will be before the write happens, right? So once you do the write and you have to read, you can't guess what the counter is going to be, because the counter is read, a unique counter is read every read. It's difficult for the attacker to decrypt the data in the PCM memory, right? So this is fundamentally what counter mode encryption is, right? So we use this concept of counter mode encryption. We say that that is how the regular systems are organized, right? And we propose something called as dues. Now, why is it called dues? I don't know. It is called dues because we didn't come up with a more creative name. We could have come up with a much better name. But we just called it dues. We call this idea dues, but you can call it whatever you want. Um, the fundamental insight here is that we re-encrypt only the modified words, right? So let's say you have a cache, you have encrypted PCM. Every time you change any words in the cache, you have to re-encrypt your entire PCM line, right? What you want to do is that you want to just re-encrypt this part of your cache line while keeping the rest of the PCM with the old encryption, right? So in this work, we are not saying that we have to not encrypt the other part. What we are saying is that we keep the other part encrypted, but using the old encryption value, right? The value that was used to encrypt the original line. The line that is changed here, the part of the line that is changed here, that is only that part is re-encrypted, right? And we use counter mode encryption for this. What we say is that, let's say that we have counters for each part. We can use the old counter values for the other parts and use a new counter value for just this part that is changed. Because the counter value changes only for this part, the encryption algorithm would only flip bits for this part, and these parts would have the, because you're using the old counter values, you should be fine. Okay, so any questions here? No questions? Okay, so the good thing is that because of this, these parts do remain encrypted, right? So good point, right? So how do you choose which part to be, you mean to be re-encrypted, right? Because this part does remain encrypted. It remains encrypted with the old counter value, right? Those counters have not changed. This part gets re-encrypted, right? And that gets re-encrypted with a new counter value. And here the new counter value has changed, right? Now the question is like, how do you find out which part is um, needs to be encrypted, right? So one thing you can do is that you can imagine this, right? So let's say that at time t equal to 0, right? This is your cache. This is your PCM, right? This is the data block. You got the data block here. Okay. When you place it in the cache, it is decrypted, right? Now it remains in the cache from t equals 0 to t equals t dash. Okay? And at this point, you write into the line. Okay, so you wrote into the line. So what you can do is that in the cache, you can add some extra bits, right? If this bit is set, it means these bits are modified. If this bit is set, then this bits are modified. If this bit is set, then these bits are modified, right? So whenever you do a write in the cache, you will track which part was modified and set the bit there, right? So you know exactly which part in that line was modified. So when you have to encrypt something, you will know that you have to only encrypt this part, because these parts, they can remain inside the memory with the old encryption, right? Now you can have many writes, so that will probably modify many parts, right? But what happens is that lots of lines, you just have one or two writes that only modify some parts of the line. You don't modify all the lines. Does that answer your question? Yeah. So how do you efficiently implement this, right? So let's say that let's say that the counter values for each of these parts are 0 in the beginning, right? Let's say that this part um, was was modified, right? It's possible that this part keeps getting modified. So your counter value from 1 becomes 4. This part gets modified a little bit. So from 0, it becomes 1. These parts are maybe slightly intensive in terms of modification. So it becomes 2 and 3. But remember, all these parts were unmodified, right? This means that this part would have 4 times the amount of bit changes as compared to this part, right? This part would have once the bit change happening once. This part and this part would have 2 and 3 times the bit changes, right? But eventually, what will happen is that everything would get modified, and you'll have to keep track of all these counters, which is very expensive because you can't have so many counters, because each counter can become very large value, right? Like you obviously are not going to just have 8 writes to a line, right? 8 writes to just part of the line. You might have maybe 64,000 writes to a line, right? 64,000 writes to just this part of the line. So it's very expensive to keep track of counters for each part of the line, right? So what we tried to do was that we tried to reduce the overhead of keeping counters at a per word, right? Here, every word has a counter. And we try to do this by just using 2 counters, right? If you have per word counter, each counter is going to be very large, and each of those counters need to be stored, right? And usually if you have to store so many counters in memory, it is expensive in terms of just keeping track of things. So what we did was that instead of having, say, 8 counters or maybe 16 counters, right, we just have 2 counters. Right? So what we do is that we do something like this, right? So, I mean, maybe this is not the right way to do it. I can probably give you a better way to do it. It's like, let's say you have 2 counters for each line. You have the first counter is called a leading counter, right, which is incremented on every write. And the second counter is called a trailing counter, which is updated every n writes, which is called an epoch. Okay. The modified bit per word will choose between those 2 counters. Okay, so there'll be a modified bit which is present for each word here, which can be used to choose between each of those counters. Right? And these counters operate in terms of epochs. So between 2 intervals of time is called an epoch, and between those 2 epochs, this leading counter and trailing counter operates. Right. So when the trailing counter equals the leading counter, you re-encrypt all the words and you reset the modified bit. So for a small amount of time, there will be a time leading counter and trailing counter would be different. But when the trailing counter reaches the leading counter value, you re-encrypt everything, right? And then you reset everything, okay? Between the epochs, right? This is the start of the epoch. Between epochs, you just simply increment, right? And you re-encrypt the words that are modified since epoch, and you set the modified bits. Okay, so it looks something like this. Let's say these are leading counters and this is trailing counter and these are the encrypted words, right? So what would happen is, let's say you modified some words in the right, your leading counter and trailing counter are the same. So you encrypt all the words. Then you just change word 0 and right? You modified only word 0 and word 7. Every other word is unmodified. In that case, your leading counter becomes 1 and your trailing counter becomes 0. Right? And you encrypt word 0 and word 7. Okay. Then you change word 4. Right? In that case, your leading counter becomes 2. Right? And you encrypt all the 3 words 0, 4, and 7. Right? So you re-encrypt even the words from the previous modifications. All modified words are re-encrypted. then your word again gets modified, right? Then your reading counter becomes 3, but see, in this set, word sign is already present. So you again re-encrypt all of them again, right? Then at the fourth epoch, right? Fourth write, we say that once you have 4 writes, your trailing counter becomes equal to the reading counter. In this case, you will re-encrypt all. So see what we have done. We have just used 2 counters. If we were to use something like the baseline system, right, the stupid approach, the easy approach, we would have to keep re-encrypting all the words every time, right? All here, all here, all here, all here. But because we are using leading counter and trailing counter, we re-encrypt the line only 2 times, right? There are several times in between wherein we don't have to re-encrypt the whole line. We only re-encrypt the modified words. Right? At some point in time in the future, obviously you have to re-encrypt the whole line, but it is not as frequent as every time you write, right? Now you have to do it every 4 times. We can change this number, make every 16 times, or maybe every 32 times. It doesn't matter, right? But this is significantly lower than doing it right. Right? So any questions here? Because here the epoch is 4, right? So you can change the epoch to even larger number of writes. Do you have any question? No question? So do you understand, right? So if you were to use the naive method of writing things, right, these all would be not there. And you would have to write and encrypt everything, basically all, every time, right? The entire of data. But now, because we are using this trailing counter and leading counter, we end up only changing and re-encrypting a few blocks of data, not all of it. Right? We do end up synchronizing everything after some periods of time, but that is say 4 or 8 or 16 bytes later, right? In between that, you are okay in just re-encrypting parts of the data. The advantage of this technique is that we only use 2 counters. We don't even have a lot of counters. Okay, you again restart, right? And again, the next epoch, word 2 and word 4 modified. So your reading counter will become 1, right? So it will become 5. From 4, it will become 5. And trailing counter remains at 4. So after some epoch, when it becomes 8, both will become 8 and you will re-encrypt everything. Right? So the advantage is that Deuce does partial re-encryption between epochs. So here the epoch is a 4 write epoch. You can keep it a larger epoch. Between the large epoch, it will only do partial re-encryption. It won't do entire re-encryption. Right? But the advantage is that even if it does partial re-encryption, the data is still secure because the original data before it did partial re-encryption was encrypted. Right? So even if somebody steals your device at this stage, your data is still encrypted. It's just that some of them are re-encrypted 2 times or 3 times, but the baseline encryption is still there. Does that make sense? Any questions? More questions? Okay. So let's see how to decrypt. In the decryption, you generate two pads. I don't want to go into details of this. What are the results? We kind of model this using some simulator. Obviously, we do not have access to like a real phase change memory at that point in time. And even if we had access to it, we had to change so many things inside the system that we obviously couldn't implement that on a real system. So we kind of modeled these components, and we try to see like what the results will look like. And what we found out was that if you were to have encrypted data with flip and write dues and unencrypted with flip and write. So if you had an encrypted data with flip and write, we roughly got like a 40%, 45% intensity in terms of bit flips per write. So the time factor for what? You mean the epoch? You mean this epoch, right? So that is decided. That was decided empirically. By empirically, I mean we ran a lot of experiments, because if the epoch is large, then eventually all the words would anyway get encrypted, right? But if the epoch is small, then you would do re-encryption every time, right? So after running a lot of experiments, we found out that epoch of 4 writes is very good generally for all applications. So that's how we kind of converged on epoch of 4. Yeah. So good question, right? Usually these things you kind of can just run experiments and try to find out. So we ran some benchmarks. And what we found out was that if you were to encrypt things, and these are some benchmarks, very intensive benchmarks, versus when you have unencrypted data, you see the mean, right? Is significantly lower in terms of bit flips, right? If you have unencrypted data. And when we used our technique, we were obviously not as close to the unencrypted case, but we were significantly lower as compared to just regular encryption. So we saw that we were eliminating about 2/3 of the extra bit writes just by a simple scheme, right? Simple scheme, just 2 counters, but a very smart way to re-encrypt things. Right? And we didn't care about what encryption algorithm was used, right? This was agnostic to the encryption algorithm, but this was a very simple scheme to kind of reduce the amount of bit flips in PCM memory. Right? And if you see the unencrypted, if you look at unencrypted data versus if you were to use encrypted data with flip and write, you can get a lot of free speed up if you were to not encrypt, right? So Deuce was kind of coming close to that number, right? Because if you were to simply use encryption, you would see a lot of slowdown, but because we were only encrypting parts of the data, some bits in the data, Deuce was getting a very high amount of speed. Right? Similarly, if you look at energy delay product, because we were flipping fewer bits, we had a much lower energy delay product as compared to just dumb encryption, right? Right. And if you look at lifetime, we're able to improve lifetime by up to 2x because we were not encrypting and flipping all the bits, right? We're flipping only a few amounts of the bits, right, between different epochs. Right? So because that is the case, we could improve lifetime significantly. Right. So summarize, what was happening was that, well, we could say that bit flips are expensive, right? And ideally, you want like 12% of the bits to flip. But PCM is prone to attacks, whereas you can steal things and you can secure it with encryption. But if you were to encrypt PCM memories, you cause an increased number of bit flips. The goal was to encrypt PCM without causing amounts of bit flips. We proposed this idea called deuce, and we were able to reduce the bits by 27%. So the goal of this entire presentation was twofold, right? I'm not going to go over the rest of the slide deck. So power is also going to reduce, right? Because I am not going to flip that. So if you look at the energy delay product, so energy delay product into account the energy also. And because I'm a fewer number of bits as compared to just the dumb encryption, you reduce the amount of, you reduce the EDP, you want lower EDP. You reduce the EDP significantly, right? Because I'm only changing a few bits. I'm not changing all the bits, right? Most of the time. So basically what I want to say is that generally speaking, this is just one problem, right? So today I focused on one very specific problem and I gave you a very specific solution. But broadly speaking, this is a very, very rich area in terms of just research. There are problems in which you kind of are looking at hackers stealing data by using something called as Spectre or meltdown attacks, wherein you use the CPU, you target the CPU, and then you use speculative execution, basically branch prediction, to actually access data in the memory and get data from other users. There have been people who are looking at um, uh, attacks which kind of look at ransomware, for instance, right, wherein you kind of encrypt your storage and the key is with the attacker, so the user can't use any of the data, so all your files just go missing and you can't do anything about it. So a lot of people at the level, obviously, we can only do some tricks like I discussed in this talk, right? Try to look at ways in which we can find things here in such a way that the CPU is smart to detect these attacks, or you encode the memory in such a way that you can somehow prevent these attacks, or you detect things in your SSD before the ransomware actually starts, right? So these are all very important areas that people are already looking at, and it will be very interesting if someone eventually in your master's or in your PhD or wherever, right? If you go to work somewhere in any of these IT companies or tech companies, look at these problems. Very, very interesting area. So that kind of concludes my talk. I don't want to go into the other areas because those are like completely different contexts. And maybe some other time when I'm giving a talk, I can describe those problems as well. But beyond that, I'm open to questions. If you want to ask me questions um, on my research on this area, anything else, I'm open to questions now.
Any questions anybody would like to ask?
Yeah, I hope you learned something. That was the whole point. I had an option of going very broad and teaching a lot of things, and the other option was to kind of go narrow and teach one thing properly. I chose to do that, teach that one thing. Yeah, thanks for that. So I think if I go broad, then it would have, given that most students are undergraduates, right? They might not understand a lot of things very well, but if I teach you one thing, it might stick around maybe for longer, hopefully. That was the intention now. So yeah, if you have questions on anything, I mean, you don't have to have questions just on this, but anything else, I'm all open.
I don't think we have questions now. Anybody, last chance now. Our all STTPs are over. VLSI. This is the last technical session. If you want to ask, you can ask. And it was a very nice presentation, Prashant, by the way.
Yeah, thanks. Yeah. So yeah, put in some work. So there are.
I'll remove you. I'll remove your presentation slides. Can I give access to our madam? Okay.
I'm just going to stop now.
So what you were saying?
Yeah, so I think there was somebody asking me like what other area of research is important. Like I think memory systems is a very wide amount. It's a wide amount of research areas, right? People at compression, right? Data compression to store more data in memory systems. People are looking at for machine learning, for instance, right? People want to store as much weights and as much actions inside the memory, right? And looking at different ways in which you can store all of those efficiently in memory systems. So at least 1,000 different areas people are looking at least in just my level, right? I'm sure that in VLSI level, in what Rathod sir is working on, and other levels, people are looking at a lot of different areas in there, right? Because think about it this way, right? Generally, a computer is composed of two things. There is and then there is memory, right? People obviously look at compute, efficient ALUs, efficient multiply and add units um, for machine learning and other things. And people obviously are looking at memory, right? Because these are the two things that your computer is composed of. So there's a lot of area research here, right? And I feel most people should come and try to. So Google Drive and all those people use some proprietary encryption tech. I do not know what they use. They won't tell you. Apply, yeah, this applies to all those places as well. So it doesn't have to apply only to. It can apply to storage and other things as well. Yes. It's very difficult to know what they're using. Almost impossible. Sir, I think you're muted.
Sorry. Are you also working on in compute memory, those kind of concepts?
I was trying. I mean, I am interested in it. I'm right now. No, I don't have any student working on in memory compute. But I think that's a very interesting area. A lot of people have tried to do this for FTMs and other types of networks, wherein I think they are more amenable to in-memory compute for in the machine learning area for inference. But I haven't, I haven't yet had any student come to me and tell me that they want on it. So usually I am driven by my students. So if the student comes and tells me I want to work on something, I will be like, yeah, fine. Yeah.
What kind of simulation tool do you use there?
So we have several tools. So for mostly it is Gem5. I think you know Gem5. Gem5 mostly for architecture simulations, but then also use a lot of area computation tools like Cacti and time loop for machine learning systems and many things, right? So the kind of tool basically depends on what the problem is. And usually that tool is basically managed by the. So I tell them to become an expert in it. So over 1 or 2 years, they become expert in that tool and they use it during the PhD and they pass it on to the next student basically.
But they are in-house design.
No. Most of it is not. It's mostly just either given to us by the industry. A lot of tools are designed by industry and given to academia. So they just give it to us to kind of use. So that way they can whatever they're doing inside it and whatever the results we present to them, they know that it's kind of internally applicable to NVIDIA or AMD or something, right? So
Like, for example, if we want to work here, we don't have that kind of an interface. No? So, what kind of tool sets are open source or freely available? If
So
somebody wants to work in compute memory or these concepts, so any tool set?
For in-compute memory, there is no tool set right now. So you will have to design your own tool set. Yeah, you will have to either take Gem5 and some other simulators and change it to kind of have those in-memory compute modules and all that inside the simulator to simulate your idea. And that is usually the barrier, right? It takes a student 6 months, sometimes depends on how good the student is, to kind of incorporate all that before the student can even start evaluating the idea that they have.
Anyways, thank you very much.
No.
Thanks a lot.
Yeah. Thanks.
It was very interesting, very nice session. It was you're a good teacher, by the way. That's what I can say. Very simplified manner you have explained. Small concept, very nicely, very nicely explained. By the way, what tool you was using for writing? It was a canvas or something else?
No. This is iPad. I use something called as GoodNote. Maybe on iPad. So you can use it on iPad and yeah. It's very. And anyway, I learned everything. I learned everything from you, so I should be thanking you for being a good teacher. So.
No, you're most welcome.
Yeah.
Kindly accept this our certificate. This is what we can do. Give it to you. That's it.
Yeah, thank you. It's okay.
Thanks a lot. We'll be looking forward for more interactions. Particularly, I'll be looking forward because now we are autonomous. So I'll be looking forward from students' perspective, something can be done. Please let us know.
Of course. So if anybody has any questions, any students have any questions, they can just send me an email or something. I'm all for it.
Okay. Thanks. So thank you very much, Prashant. Now, yeah. So I have few instructions for participants. That's it. You can leave the meeting if you want.
Yeah. I might. It's a bit late here, so I want to stick around, but I think I
No, done. It's over. Our session is also over. I'm going to close this meeting.
Okay. Thank you.
It was specially scheduled only for you. Okay. Thanks.
Okay.
Okay. Thank you very much. Thank you. So, yeah. So participants, we are going to meet at 2:00. Please join 5 minutes early. That will be good. 5 to 10 minutes early if you join, because we know resource person is going to join on time, and we don't have anything as such to start for the session. We will directly start with his speech. I'll introduce him, and we'll directly start with his session. And once his session is over, then hardly in 5-10 minutes, we will start with the certificate distribution. So it won't take much time. Please join at 2:00. That's the last session. So that's what my request is. An entire material is available on Moodle. Whatever slides, like Prashant has also given is a lot of material, good slides. That also I have put on the Moodle. And those who have given the material till date, everything is available on Moodle. So you can download it from there. Today's quiz is closed, so you will get your score also there. Everything is done now. Only certificate distribution remaining, last session. So most welcome for that last session. Please join. And I request few of you to give the feedback. If you have been asked to give the feedback, for 2 minutes, you can unmute the mic and you can say whatever you want to say, you can say. Okay. So thank you very much. I'll close this meeting. Then thanks a lot for joining. We will meet at 2 p.m. Photo. Please, we will take a photo in between. This time, we would like to have a guest also with him. You unmute yourself. आता घ्यायचा का मॅडम नाही ना? Not now, right? स्नेहा
No
मॅडम?
sir, नाही सर आता नाही रिमाइंडर द्या असं बोलत होते.
Reminder. Okay. Reminder. Please unmute. This is our sincere request. इतना तो कर ही सकते हैं आप. कैमरा तो unmute करके बाबू.
Kindly unmute and kindly turn on your camera and give the feedback. So we have a guest, a very special guest today. So that's our request.
Yes. Please. Thank you. Sneha madam, we will meet on other meeting.
Yes sir, just give me just 5 minutes.
Yeah.
Okay sir.
Yes, sir.